Hello everyone. With this video, we are going to start our final module in this course, and this module is going to give you a high-level view of different concepts in the area of transactions and concurrency control techniques. Okay, so what is a transaction? So transaction is any unit of program that accesses different data items, either reads it or reads it and then writes it and so on, right? So this is a transaction. Even your typical SQL queries that you have been firing on your database, select star from this table where this clause and all, those are also actually transactions. So each SQL query is a transaction at its lowest level in a typical implementation. Uh, and even when you do, let's say, update statement or delete statement, they all are samples of a transaction for a database, right? And but these are individual queries. You can in fact club together different SQL queries into one transaction also, right? So that your databases allow that, right? So what we are going to do is that in this particular module, uh, rather than talking in terms of tables and all that, we are going to talk at a much more fundamental level of having a data item. Those data items could be such things like your account balance, or maybe number of free tickets available or something like that, right? So we are going to talk in terms of data items, and we will talk how different transactions may try to access data items concurrently, such that some guarantees are always ensured, right? Because at the end of the day, in your system, where it's a multi-programmed system, different users are accessing it simultaneously, you need to have some guarantees that your answer will always be correct and so on, right? So we will go much more detail on what do we call as correct, right? So this definition of correctness will also change, right? Okay, and depending on certain definitions of correctness, you will have certain algorithms to achieve that level of correctness, right? But okay, we'll go step by step. Okay, so here I'm just illustrating a very simple transaction, right? So in this transaction, what we are doing is we are transferring $50 from an account A to another account B, right? So $50 is transferred from account A to account B, right? So I'm calling this as one transaction, but if you were to go ahead and implement this at the in your database application or so, right? This will be couple of SQL statements, right? So first this will be just like select star from where clause kind of SQL statement. Then when you take out $50, then again you have to update the balance. This is another SQL statement. And then finally this write. So this is another SQL statement, right? So it's couple of at least 3 to 4 SQL statements depending on how you implement it, right? So this is what I was saying, that a transaction at its fundamental level uh, can be one SQL statement, or it can be a collection of SQL statements also, right? So your in your database, it allows you to define such that in this way, right? Okay, so this is an example of a transaction. I'm taking $50 from account A and then I'm depositing it into account B, right? Now let's try to see what kind of properties should I have in my system so as to ensure some level of sanity guarantee that we can give, right? So the first thing is what we call in our database terminology as the atomicity requirement, right? So atomicity requirement states that a transaction such as this, you're taking $50 from here and depositing here, uh, atomicity requires us that a transaction either executes completely or it does not execute at all, right? So for example, in this case, if the transaction sort of, fails midway here, after this, right? So then what has happened, you have taken out $50 from account A, but you have not submitted that money in account B, right? So in the middle, there can be some network error or a system crash or something can happen, right? Uh, in such a case, what has happened is that, you lost money in the thin air without getting transferred to anywhere, right? So this is not good, as you can guess why, right? So this is what is called as the atomicity requirement of a transaction, right? So by, just to give a formal definition, atomicity requirement states that a transaction either executes completely or it does not execute at all. So there is no partial execution allowed of any transaction, and and it's completely up to you to define what your transaction is. It can be one SQL statement or it can be couple of SQL statements, right? So if you want a transaction to be couple of SQL statements, like, over here, read the balance, then write the balance, then update this balance, right? So if all of this is a transaction, either all of these SQL statements will execute or none of them will execute, right? So this is the atomicity requirement. Second, durability requirement. So durability requirement of a transaction, uh, it's defined as the following. So once the transaction has been completed and the updates are returned to the database, those updates must persist for the time eternity, right? So a classical example of this being that, let's say you booked a railway ticket, right? And when you booked the railway ticket, you got your, ticket output, right? And then the fact that, and when you get your ticket, we can sort of say that, your transaction has completed and you have been issued a railway ticket. Now, even if the database at the IRCTC crashes or something happens to that server, the fact that you have been issued a ticket should not be lost in the system. Now, it can be a software failure or it can be a hardware failure also. Doesn't matter, right? So this is what is called as the durability requirement. Once a transaction has been completed, and there is a very formal definition of what we call as completed, right? So once a transaction has been completed and the updates have been written, those those should persist in your system for time eternity. You should never lose the information, right? Even if your disk crashes, right? So there is a whole module of the database system called as recovery manager, which takes care of durability a whole lot. But I don't think we can cover that in this course, but, just some information that you know, right? Okay, so hopefully you understood what is durability requirement. Another example that you can think of this is that, let's say, you transferred money from account A to account B, right? And then you got a green signal that, the money has been transferred, right? So this transaction, the effects of this transaction should be there in your database, right? So tomorrow, if your system crashes, uh, data, the account balance of A and the account balance of B should not go back to their old values, right? They should still be the last sane value, which is according to the transactions which have been done on that, right? So that is the durability requirement. Okay. Next is consistency requirement. Okay, so consistency requirement is not uh, so much concerned with the database, the physical model of a database, but it's more on the level of application program developer, right? So consistency requirement of a transaction states that at the start of the transaction, if you are seeing a consistent uh, state of the database, then after your transaction is completed, you should leave the database with another consistent state, right? So this basically, boils down to the fact that, whatever logic you are writing in your transaction code, it should, it should not do some crazy things. So for example, your transaction should not be that you take out money from an account but don't deposit anywhere, right? So that leaves your database inconsistent at the end of the transaction, right? That is not good. In summary, consistency requirement basically states that whenever we are coding transactions, we have to be a good programmer, right? And we should not have erroneous logic in our transactions. Next. Okay. So isolation requirement basically is concerned with the concurrency requirements of a database system. Let's say there are several transactions which are running in your system concurrently, and isolation requirement states that each transaction should be sort of unaware of other transactions which are running in the system, right? So let's take an example here. So you have two transactions, T1 and T2, and in T1, I'm reading this value A, subtracting something, then again writing it, then again reading B, adding 50, and then again writing B, right? So this was that our old example of transferring $50 from A to B, right? And then there is another transaction T2 which wants to read data item A and then read data item B and then print A and the sum of A plus B, right? So these two transactions, clearly they are not independent in the sense that they both are trying to read and write the same set of data items A and B, right? So if T2 was accessing completely different data items, then this is sort of trivial, nothing special over there. But in this case, T1 and T2, they are not entirely independent. And let's say that and in your database system, transactions are executed in an interleaved fashion. Let's say that your system first executed these three steps, and then in the midst, let's say that T1 got descheduled, and then again T2 got scheduled, and then and it did these three operations, right? Now what will happen is that and now then T1 came back and it finished uh, these parts, the last three steps it finished, right? So now this is undesirable. You can guess why. Because what has happened is that this value of print A plus B, right? uh, so this value should be same whether T1 executed before, whether T2 executed before T1 or after T1, right? So that would have been the ideal case. But if you are you know scheduling operations from T2 in the between step 3 and 4 of T1, you are going to get erroneous results, right? Because you have deducted $50 from A, but you have not really deposited $50 to B, right? So this is not advisable, right? Trivially, you will always get a good, correct result if you are if you are executing your transactions serially. By serially, I mean that if whenever you have transactions T1 and T2 like this, you either first execute T1 or you first execute T2, right? Then it will always be good. If T2 is executed first, then you will get some value of A and B, and then print A plus B. This will be okay, and then T1 will be executed. If T2 executed after this, you will get again and good sane values, right? But if T2 is sort of executed in the middle between 3 and 4, then you're going to get some kind of a garbage value, so to say, right? So serial execution of transactions is always good, but what happens is that when you are trying to design a system, let's say at Visa payment services, right? So millions of transactions happen every minute, right? And if you're trying to execute your transactions serially one after another, your throughput is going to go down, right? So there is a whole area of research and even technology which has been developed along this idea of isolation requirement, and this is where the concurrency control techniques come into picture, right? So what people do is that we people design the concurrency control techniques such that they do allow interleaving of operations between two transactions, but still they guarantee uh, the following statement. What they guarantee is that each transaction is sort of unaware of any other transactions which is executing concurrently, right? So another way of saying it is that intermediate transaction results are always hidden from other concurrently executing transactions. I think this is the summary statement that you should take for your isolation requirement of a transaction, right? So if you just want another way of saying it, let's say there are two transactions ti and tj. Your final result, I'm going to use the word result under quote and under quotes. The final result will appear such that either T1 executed first or TJ executed first, right? So the final result will look like that, even though you have your database system is allowing for interleaved operation, right? So I'm going to use the, as I said, I'm going to use the word the final result in quotes because there are different definitions of what the final result means. Okay, we'll get more into that, but for now you just take this part. Intermediate transaction results must always be hidden from other concurrently executing transactions, right? So for example here, when T1 was doing this transaction and got descheduled and T2 was picked up, this read A which T2 is going to do should not be this value. It should be the old value of A, right? And then there are a lot of concurrency control techniques which ensure that, right? So that's what we mean by saying that if you are picking up in the middle of this, then you should not see the intermediate values of T1. You should see the values before T1, right? Okay. Or if your concurrency control happens, if different kinds of interleavings are generated, this view can also be after the value of A after this transaction has finished, right? Okay, I think that's enough for now. We'll go forward and we'll cover isolation much more, right? Okay, so I'm some sort of summarizing all the properties of a transaction that we just discussed, right? The first one was atomicity. That means we said that all the operations of the transaction must be executed or none of them should be executed, right? So in other words, there was no partial execution allowed. Consistency, we were saying that we should have a good transaction logic such that each transaction takes the database from one consistent state to another consistent state. Isolation, we want our database system in a way that each transaction is unaware of other concurrently executing transactions. In other words, if there are multiple transactions which are sort of trying to access the same data item, then you have to maintain some kind of an semantic ordering among them. Okay. And then lastly, durability, which means that after a transaction is completed and the changes has been made to the database, then those changes should be present in your database even if there is an hardware failure, right? These four requirements, these are called as the acid requirements of a transaction. It's a very famous question, right? People will ask, what are the acid properties of a transaction? So these are your acid properties, atomicity, consistency, isolation, and durability. Okay, and now the database system is actually designed to address these things. So atomicity and durability, these two properties are addressed by the recovery manager of a database system. We'll not have time to cover that in this course, right? But just so you know, atomicity and durability are handled by the recovery manager. Isolation requirement, which which is what I said, that ensures that intermediate results are hidden, and you don't get garbage values when when transactions are interleaving, right? So this whole of isolation requirement is ensured by the concurrency control manager of your database system. So we'll cover isolation again. I cannot cover all the uh, concurrency control techniques which have been taught, which are there, uh, but hopefully we will be able to cover the most basic ones. Okay, let's go forward. Okay, I think I already covered this. Okay, in next couple of slides, what I'm going to do is that I'm going to show you some examples to illustrate the importance of the isolation requirement, right? So in the okay, so let's see this. Okay, so let me go back a little. Yeah, so we have two transactions here. So transaction T1 is reading a data item X, subtracting something, and then uh, you know and then writing data item X, then again reading Y, and then adding that value, right? It's sort of transferring money from account X to account Y, right? And then there is another transaction where you are reading the same data item X, and you are incrementing X with a value N, right? So this could be transferring N rupees from X to Y, and this could be that X just got some extra money into it, right? So these two are very valid transactions in themselves. Now let's see some cases where if we are not having the isolation requirement uh, in our interleavings, then what kind of problems can come up, right? Okay, so let's see this first. Okay, so let's say that these two transactions, they were executing in an interleaved fashion, and this was the interleaving which got created, right? So you by the way, you have no control on the interleaving, right? So this interleaving will depend on a lot of parameters, like what is your CPU scheduler, right? You have no control on when the transaction gets descheduled, right? So if you have something like a round robin which deschedules a process after every few milliseconds, then you have no control on what the interleaving will be, right? Now all we are going to do is that if we are not ensuring our isolation requirement, then what kind of interleavings among T1 and T2 are troublesome for us? That is what we are going to study. Ideally, if the entire T1 was executed before T2, or the entire T2 was executed before T1, no problem. But when we start to have interleavings, some interleavings are problematic. And then let's see examples of that. And these are the kind of things which go against the isolation requirement, right? Okay, so let's see this interleaving. So here you already read the data item X, you subtracted some value N, and then again you read this data item X, and you added this value M, right? And then you wrote this data item X, read the data item Y, not a problem. This guy is a problem. When you perform this write operation on X, what has essentially happened is that this update of X getting decremented by N rupees, that is lost. This is called as lost update problem. So the reason this happened was that when when we read this data item X, when we read this data item X, no, we read the old value of X only, right? So this is in contrast with the earlier example that I showed here. Right? So this example is different from the right. So this is a different example. Remember, so here I was reading from this only, right? So this was also problem, right? And what I am saying here is also a problem, right? So here X was, both T1 and T2 were reading the old value of the X. T1 was making a change. T2 also made a change. Then what happened is that, when we wrote this guy, we have essentially overwritten the changes made by T1, right? So this is what is called as an lost update problem. So another example of what should not be allowed in an uh, under the isolation requirement. Okay, now let's see another example here. So in this case, what has happened is, T1 has, done, it executed the first three steps. It read data item X, made some updates, and then wrote the data item X. And then T2 has consumed this value. It whatever it is reading X, it is going to consume whatever T1 has, thrown out as the output, making some changes, and then again writing, right? And then T1 proceeds, and now it so happens that T1 transaction crashes for some reason. There can be n number of reasons for its crash. It can be hardware failure, or it can be some null pointer exception, or some exception which can happen, right? And as a result of that, the T1 is going to be effectively nullified, right? So that is okay, but what happens to T2? So T2 has now consumed the output of a transaction which is going to be nullified, right? So this is what is called as a dirty read problem. So T2 has read something from the output of a transaction which is going to be cancelled or nullified, right? So this is what is called as a dirty read problem. Something like this should also be avoided, right? Because what now happens is that if this is rolled back because of an error, T2 would also be forcibly rolled back without any of its fault. Okay, T2 is going to be rolled back just because it consumed an value from an transaction which is going to be rolled by, right? So this kind of a dirty read is what we call in our database literature. Dirty read is not good and should be avoided, right? So an ideal concurrency control manager will avoid these kind of things. Okay, let's go forward. Yeah, so yet another example. I think this is called as the incorrect summary problem. So there are two transactions. So T1 is your same transferring 50 rupees from X to Y, and T3 is a transaction which is sort of summing up all the account balances in your branch, or let's say, right? So now what happens is that this is a big transaction, right? It is reading a lot of account balances and creating the sum, right? Now what happens is that if these transactions are processing in the middle, that transferring money from one account to another, right? You will not get a correct sum, right? So over here, so so over here, what has happened is I am reading X after $50 has been subtracted, but I am reading Y before $50 has been deposited here, right? So this kind of a thing will lead to incorrect summary, right? So and just another example of what should be avoided in an under an isolation requirement of the databases. Okay. Okay, so as I mentioned before, concurrency control techniques, they are basically used to achieve isolation, and they try to avoid all these problems, right? Now, of course, in your modern day databases, this definition has been sort of stretched, and people have relaxed it to some extent to get a better performance and all that. But we will cover the most traditional formal definition of isolation. Okay, let's get started. Okay, so again, we have two transactions. A A trying to send some money to B, and then there is another transaction over here which is also making updates to accounts A and B, right? So far we saw examples of what kind of interleavings are bad, right? So now let's try to go back and see that, are all interleavings bad? Certainly not. There are some interleavings of these two transactions which are not so bad. And what is a formal definition of the interleavings which can be considered as good? So trivially, you can say that, given any two transactions, which sort of share the which sort of perform read and write operations on the same set of data items. Those two in the interleaving, which is essentially serial, is always good, right? So, for example, these two transactions, if you execute T1 first and then T2, or first T2 and then T1, this kind of a serial execution is always good. But as we said that, we don't want only serial schedules, right? We do want some interleavings, right? So now let's try to see some example, at least, one example on what kind of interleavings are actually good. So watch this interleaving very closely here. So here, so T1 reads data item A, makes an update and writes data item A. So T2 reads data item A, makes an update and writes data item A, right? So here, of course, that dirty read problem is still there. But if you set aside the dirty read problem for maybe just few minutes, then let's try to see if the uh, other interleaving which is getting created, does that make sense or not, right? Of course, transaction T1 commits over here, but when T2 was allowed to read this intermediate output, T2 had no idea whether T1 is going to commit or not, right? So this is still a dirty read problem, but if you let go of the dirty read problem, at least for now, let's see uh, whether this interleaving is going to be okay or not. Okay, no, so this happens, and then you read data item B, make an update, you write data item B, and then again you read this, again B is updated, and then you write data item B. Okay, now the question that we ask is that, this interleaving which has been sort of allowed by your concurrency control manager, what is the end result of this interleaving? So if you watch closely, the final output after this interleaving will be same as the interleaving which is given in this slide. Okay, so here T1 first read data item A, and then T1 was also the first transaction to read data item B, right? And then T2 executed after the entire T1 execute, right? Again, as I said, ignore these commits for now, right? So just these operations, if you see, this is how they executed, right? And as we say that serial schedule is always the gold standard. A serial schedule is always correct, right? So depend the final output will still change whether T1 executed first or whether T2 executed first. The final output will still change, but that is an output which is always semantically correct, right? So it's like this, you just have one train ticket and then two people trying to book that ticket. Now, if person A gets first, he will book the ticket and B will not get it. But if person B was allowed first, then B will get that ticket and A will not get that ticket, right? So that permutation is always, it exists in the real world, and that is a permutation which we all agree that it is semantically correct, right? So that part is there, but all we want to ensure is that, whatever interleaving is being generated uh, by your concurrency control manager, that is equivalent to at least one serial schedule, right? Now when I say equivalent, I'm going to, underline the word equivalent, and there are multiple definitions of what I mean by equivalent, right? So we will cover something called as conflict equivalent. We will see what it is, but the summary statement being that your concurrency control manager strives to get an interleaving, or if I'm being very careful, because interleaving is actually not in the hands of the manager, rather than concurrency control manager prevents a certain kinds of interleavings, and whatever interleavings are sort of not prevented by your concurrency control manager, those interleavings will result in a final result which is equivalent to either T1 executing first or T2 executing first. That is how I would like to put as the formal definition of what a concurrency control manager does. Uh, you know it it has no power to execute these three first and then these four. This is dependent on your CPU. Concurrency control manager only stops certain things. The final interleaving can be anything, right? But the goal is to ensure that whatever interleavings are sort of allowed by the concurrency control manager are at the end of the day equivalent to either this where T2 is executing first, or equivalent to this where T1 is executing first, right? Okay. So in the next video, we are going to talk about more about what I mean by equivalence, right? So there's something called as conflict equivalence and all that. We'll see about that.